Hello everyone, can you hear me? Perfect. I heard there's like quite some competition in the next room in terms of popularity of speakers, so I appreciate that you found your way here. Who am I? I'm Robert Kubis. I'm a developer advocate for the Google Cloud Platform. So we basically understand our job being a bidirectional connection point of you guys into our organization. So you can always reach out to me on @HostyRosty on Twitter or through GitHub or through Medium or other channels. We love to collect feedback in terms of like what we can do better or ideas that you have, how you use our products. We love to promote them. What am I going to talk today about is a new approach of data processing, and you might have seen the discrepancy in title of my slides to the one that is on the schedule, so I want to address that really quickly. So if I see or look at user experience, to improve user experience, there are a couple of steps that you have to take. First, very simple and different methods that you can do that is collecting data, and I'm not going to talk about how you collect data today. The second step is analyzing that data that you have collected and then taking the insights that you have out of this analyzation and applying them in a way of like improving your application. Now, today's talk is about looking at like what that can be. It can be on the one hand stream, like events that come in that you collect, be it a click stream or any kind of telemetry data that you collect for your application, or it can be batch, where you basically collect data for over a time frame and then you process that data in a batch mode. And today I'm going to talk about analyzing data. That is the topic. So if that's not what you expected, feel free to choose another talk. I won't be offended. But first, I want to go a little bit in the history to get everybody on the same page, like where we are coming from. Now, if you look at data processing at Google, there's like a long history of different kind of frameworks and methods that we've developed over the year to cope with the amount of data that is collected. And as you can see here, the timeline starts about 2002. And Google was founded in 97. The reason was we were really, really scrambling the first couple of years. We didn't have time to write papers or think about novel approaches. So by the time that we could actually breathe a little bit and think about like, okay, how can we approach data processing in a better way? That's where Jeff Dean came up with a model like where he saw like our software engineers are doing the same things over and over again, and they are dealing with distributed systems in a way that they shouldn't be. They shouldn't care about like how our data processing programs are running, and they shouldn't care about like dealing with failures and things like that and resiliency. So he came up with a model and formulated that as MapReduce, which takes care of like failover and things like that. So what is MapReduce? Basically, MapReduce is a batch processing of data. So you have a big batch of data, you split that data up into chunks, you apply a mapping function where you pick out a key out of these chunks, from each element in that chunk, and then you shuffle it around, and then you have so-called reducer nodes where you put these keyed elements, and then the reducer applies like an aggregation or any kind of grouping function. And then you have like your insight at the bottom, and you store that somewhere. Now the problem with map and reduce is usually what you do is you don't end up like writing one program and then you have your answer. Usually you have to pipeline these batch programs. And again, like what they ended up with was like a lot of developers did the same work of like moving data around from one batch process to the next one, from one MapReduce job to the next one, and repeating over and over again the same kind of data. So they wanted to come up with a framework where they deal with this as well, and that is where Flume Java comes in. So 2010 we publicized a paper about Flume Java, which basically gives you a higher level API to write MapReduce jobs and pipelines of multiple MapReduce jobs. So it's basically a graph of transformation that you write. It's still batch, and the code looks a little bit like this. So you basically have a P collection that you can process in parallel. You apply the parsing, which is basically my map function, where in parallel say like, okay, I want to have the parsing of my elements. And then you do a grouping function, which you see down there, the mean double, where I basically group per key these elements together. And then you can write that in multiple different fashions and have your output at the end. Now, Flume Java was great, and we taught that to every nuclear at Google, and everybody started writing Flume Java. The problem, there's still a couple of problems. If you look at data is really big. And the problem with this is, like, you're not really done at that point, like processing big data. Like if you see, like we chunk this up like by week or by day or maybe by hour. But the problem of this is like you do the calculation and then you have to wait for that amount of time till you get your answers, and you want to have answers faster. So the very first problem of batch is really the latencies that you have of like processing your data. Depending on the boundaries that you set, like the batches that you put, like the boundaries that you set for your data, how you split up your data, that's basically your latency at least that you end up with. Of course, on top of that is the processing time that you have. So another problem that you see is if you do this artificial splitting, so for instance per day or per hour, you end up splitting for instance, your user sessions. So if you want to get insights about how your users are using your application, that usually doesn't adhere to these boundaries that you artificially set and split your data into. What you end up with is incomplete data. And then if you calculate that, you basically get incorrect results. So what you're really looking at in data is it's actually unbounded. It's continuous and unbounded, and we somehow have to deal with this continuous and unbounded large amount of data that you're collecting. Now, a really problem there as well is that usually data is not in a way that it is happening and immediately in your processing machine. Right? There can be delays. Imagine you have like a game that supports an offline mode, and your players go on an airplane and they put it in offline and play on the airplane, and then they arrive in San Francisco 11 hours later and they turn on the phone again, and now suddenly all these events are streaming into your system. Now they are like way delayed from when they actually occurred. And to get correct results, you have to basically deal with this delay. Right? So how do we do that? That's where MillVia comes in. So MillVia basically looks at like how do I work with streaming data. And the MillVia paper basically came up with a directed acyclic graph of elements where you basically stream elements through, and then you do per element calculations. You group them into so-called windows, and then you do calculations at the end. And MillVia for you manages like state and persistent flow of all these elements. So first, of course, like what can you do? Element-wise transformations is filter that you filter based on certain key elements. And then you aggregate them in windows that can be time windows. It can be session windows. And it can be like here, event time-based windows. So here's like where you see already that we do this differentiation between processing time and event time, where we say, okay, we don't do the windowing based on when the elements arrive in our machine. We do the windowing based on when these events have happened, and then put them into the window. Now there's a challenge at that approach. The thing is, like, how long do you keep these windows open? Right? In the end, like, if elements come in like hours later, and you want to account for that, do you keep this window open for hours? What happens in that case is, again, that you have a large delay in getting your results and insights out of your data. So you have to kind of find a middle way, like, when do I close a window? What do I do with like late arriving data? And we're gonna look into that, how to do that. And what I mentioned before, like another way to window your data is sessions, where you basically don't use a time window, but you use session windows. And again, you have to decide when you close them. So if you look at event versus processing time, in this graph you see like processing time on the y-axis and event time on the x-axis, and we have this dashed line that goes like up there. Now, if you find any events in the lower right part of this graph, please find me afterwards. I get you a good paycheck. So if you find any elements in the lower right part, it basically means that you can look into the future. You're processing your data before it even happened. So the ideal world is really like that the elements are on that line. That would mean that an event happens and is directly processed. So you have no delay between processing and actually event happening. Now the reality, of course, looks different. And the reality looks more like the red line that you see there, which we call a watermark. And the watermark is something that we use basically to make a decision when we think that the majority or all events have arrived in the system so that we can close windows. So what are the motivations for streaming versus batch? So there's three main areas that you're looking at. First, completeness. Second, latency that are addressed, like batch mode latency or streaming latency. And then cost, like how much money do you invest to get low latency or completeness, correct results. Now have a look at a couple of different example or use cases here. So the first one is a billing pipeline. And I want to point out one thing here. We have a graph which shows from not important on the lower end on the y-axis to important on the higher end of the y-axis. Now, if you see in the middle the low latency bar, if that is low, it doesn't mean low latency. It actually means that low latency is not important. Trips up a lot of people, me as well in the beginning, so I want to point that out. So in the billing pipeline, what is important is completeness. You don't want to overcharge your customers, and you don't want to undercharge them because that's bad for your business, right? So you want to really make sure that your billing pipeline is correct. So that's really important. Now, it doesn't really, it's not super important that you charge them a day after the cost secured, or if it's like 2 days. Right? So latency is not so important in that pipeline. Low cost, again, is not that important. You want to be correct in this pipeline, so you want to invest some money that you are actually correct in that. Now, what is nice is for user experience, for instance, is if your users see on what trajectory they are in terms of the cost that they are incurring. Now, that is something where you want to have like an estimate. The accuracy is not super important. It still should be in the ballpark of where they end up. You shouldn't have a trajectory of 100 euros and then or Swiss franc and then end up with 1,000 at the end of the month. But if it's like 950 versus 1,000, that's not like a big difference. But you want to be somewhat correct. You want to have low latency. So the trajectory should show like pretty close to when you accrue the costs. So the person sees actually the trajectory. And you want to have low cost in the sense like you don't want to invest too much money into the pipeline. It shouldn't eat into your margin like all the way. And a third use case is abuse detection. Now, for abuse detection, completeness is not that important. Low latency is very important. So, like, if your systems are abused, it incurs cost for you that you cannot charge anybody for. So you want to detect that as fast as possible. Now, of course, you don't want to interfere with your customers in that sense, that you basically constantly name your correct and valid and proper customers as abuse customers. So still like somewhat important in terms of like that it's correct, but low latency is much more important in that case. And low cost in terms of that you can run that like really fast, but again, here also not that important. You want to invest some money because if you prevent abuse, it basically doesn't cut in your margin. All right, so if you look at historical systems, how that was solved, like these use cases that we looked at, you look at something so-called lambda architecture. where you basically looked for the correct results where we need it. So for instance, like billing, the billing pipeline, you used like a Hadoop system, for instance, or Spark system, where you calculated your billing in batch processing. Now for your live estimates or for your abuse pipelines, you used like an Apache Flink or Apache Storm, which is like a stream processing. The problem of this is your developers or you have to learn two systems, right? You on the one hand learn Hadoop or Spark, and on the other hand you learn Flink and Storm to accomplish both these challenges. Now it would be nice to actually combine that in one and only have to learn one programming model. And that's where Dataflow and Apache Beam comes in. So Apache Beam and Dataflow combines basically these two worlds of batch processing and stream processing into one programming model. So you have to learn one programming model and you can do both. So how does Apache Beam or Dataflow do that? First, before I go into the details, I want to talk about what Apache Beam is. So Apache Beam is our Dataflow SDK that we donated to the Apache Foundation to create an ecosystem which allows you to write pipelining, like data processing pipelines, which are portable. So you can basically write a data pipeline in Apache Beam and you can run it on Spark, you can run it on Flink, you can run it soon on Gearpump, or you can run it on Cloud Dataflow. So this removes basically the login. You can go where your pipelines run the best. And it builds a higher level abstraction. So it's a set, like this SDKs, you have a set of higher level abstractions and APIs that you can use to build your pipelines, which makes it much easier. And you don't have to deal with machines or things like that. You don't have to deal with failovers or resiliency. That's all handled for you. All right, so let's take an example of how Dataflow or Apache Beam, the programming model, achieves correctness in a streaming mode as well. So here in this example, we have, for instance, a game that you play, and these events happening throughout the time, and we have the real-time line there that you see there. Now, the event number 3 is like occurs at around 12:05, or after between 12:06 and 12:07, and arrives in the system shortly after 12:07. So that's pretty close to the real-time line. And then you see other events like the event number 9, which happens at 12:01 and arrives in the system at 12:08. So there we have like a 7-minute delay. Now there are 4 questions that we want to ask to get correct results and what the Apache Beam model revolves about. So first, what you know already from a MapReduce job is like, what do you want to calculate? So that is your, like, do you want to do an aggregation about like team statistics or player statistics, how many points a player has achieved over a time frame, or if multiple players are playing in a team, how much points did the team achieve? So that is like your what. Next is where in event time do you want to calculate your results? So the where is basically what do you do, how do you construct your event time windows? So for instance, I want to have like the team scores for everybody between 12:01 and 12:02. So 1-minute window, and I want to know like who was the best in that window. The third question that we ask is when in processing time is this materialized? So that deals with like when am I emitting results? When do I give like results, aggregated results downstream to like systems that I can display? Or if you look at like applications, like somebody that can act on the results of this aggregation. And number 4 is how do you deal with refinements? So there are multiple modes of refinements that you can look at in that model. One is if you have very large windows. So you look, for instance, at an hour window. You don't want to wait an hour till you get results, right? Like we're talking about streaming system, we're talking about real time more and more. We want to have like lively dashboards. But we still want a window, like we still want to use 1-hour windows. So the way that you can do is you can like emit, for instance, early results or late results, and we talk about like how you do that in the Beam model. All right, so let's start with the what. The what, very familiar to the ones that have used MapReduce. You can basically do a parallel do on elements. You can aggregate. You can do composite of aggregations and element-wise transformations. Now in the Beam model, how does that look like? So we have here, for instance, P collection that we read from some kind of data source. That can be in Beam. You have very many connectors that you can connect to. That could be a Kafka, it could be Cloud PubSub, it can be anything. It can be a file, for instance, in batch mode. Then you apply your calculation. So that looks very familiar to what we have seen for Flume Java, and then you do your aggregation. And because I want to do live demo later, I'm gonna show how that looks like in Beam. So in my demo, I show you in like throughout the talk, I have a little game where you get assigned a color, and you get 4 fields, and you can hit on these fields. And I calculate a success rate, like how successful you are in terms of like missing or hitting the right color. And then we calculate also team stuff. So if everybody of you joins in to play this game, we see like which team wins for the day. So what I get as an element every time that you hit one of these fields is basically a timestamp of when that happened, the color that you were playing for, and an ID of your player. And I stream this data in through PubSub. Now, the first question that we asked is like what we are calculating. So I want to calculate 2 things. First, I want to calculate the player statistics. So that is basically this, where I basically pull out the player ID that I give you, that we see here. Then I group everything that I have windowed by this player ID, and then I calculate the player stats. So we can have a look at this. Very simple, and you see there that we support Java 8 and Lambdas as well already. Basically, I pull out the team, I also pull out the device and the color, and then basically calculate the stats. It's pretty straightforward. All right. So the second thing that I calculate here is the team statistic that we see there, where I basically just calculate based on the team color. Now, when do I emit these results? That's where we come to the next question. But before that, so if you basically do that, like just ask the question of like what am I calculating, then we are like at the traditional batch processing. You process everything, and you get the results at the end, which would be here in that case at 12:10. But I want to get my results earlier. I want to cut down the delay till I get my results. And we have talked about there are a couple of different ways to window this. In this case, we use fixed window. So let's see how that looks like. So what I apply is to my incoming stream or batch data, I create a window. So in this case, I window that into 2 minutes. For the game, we window it into 5 minutes. So I apply this window and then say what I want to do for that window. In this terms, I aggregate, want to have the sum. So now, as you can see in this graph, so we have our slices of 2-minute windows, but we still see that we have to wait till the end of everything till we get actually our results. We're still not emitting, we still did not cut down on the delay on when do we get our results. The only thing that we did here is we now know who was the best, which team was the best in that 2-minute window. So we get a bit nicer results, a bit more lively result in the sense that we get we see the variation, but we don't get the results earlier. So that's where the when comes in. When do I want to process this? So when do I want to actually trigger? When do I want to emit the results? And as we can see here again, we take this watermark, which is a heuristic, based on when the elements come in. Like we have, it's based on the source that you're using. Can give you a heuristic when you're emitting the results. So you go through, and then once the watermark is hit, you start emitting these results. So how does that look like in Beam? You basically define triggers, so-called triggers, and you have different kind of triggers that you can use. The SDK comes with a wide set of triggers. And what we use here is, in this example, I want to trigger a result after the watermark basically passed. So I use after watermark, past end of window, and everything else stays the same. So how does it look like? In this example now, we see that the watermark basically passes and we are emitting results much, much earlier. So we can see basically much earlier like which team is leading, and we don't have to wait anymore till like the entire thing is finished. So how does it look for our demo? So what I have here is basically in the beginning, I'm reading from my PubSub, and because I might want to do some calculations at a later point, the first thing that I'm doing is I'm writing them to BigQuery, so just to archive them. So I stream basically the data, the raw data, directly into BigQuery. So now we saw the first, like, we want to window that. So the first thing that I want to do is we want to window these elements that come into 5-minute buckets. Now the next thing that I want to do is I want to add the triggers. So that was my when question. And the first trigger that I want to do is I want to emit results at the end of the window. Now this we just saw like gives me results once. But it doesn't account for like what if I want to have earlier results, what if like events come later. We saw in the beginning that events can be unbounded and can be delayed. So I still have to like refine somehow like what do I do with data that comes in late. And that is where we come to the fourth question, how do refinements relate? So what we want to do is, on the one hand, if my windows are very long, I want to say like, okay, I want to do some early firings. So you see here with early firings after processing time, where I say like, okay, after 1 minute, I already want to emit a result. So I want my team stats emitted every minute. So this is an estimated result. The next thing is if elements come in late, what do I do with the elements that come in late? So you see here with late firings, after pain.element count at least 1, that basically tells me like when do I trigger when late results come in. So after pain, basically if I started my window, if I closed my window, if there are any elements coming in this case already if only one element came in, I already trigger again the calculation, basically the grouping. Now you can define like maybe you don't want to emit a new result every time an element comes in, so you can basically say, okay, I only aggregate again after each 5 results, or you give a certain amount of time. And then we have to define, like we don't want to keep our windows open forever, because at some point we would basically run out of memory in our streaming pipeline if we would keep all the windows open forever. So you need to basically define also the stop boundary when we close the window, and then basically if then events come in later after that, we basically discard the window. So that is where with allowed lateness comes in, where you basically say, okay, in this case, I want to close the window after 10 minutes. If any event comes in after 10 minutes after I close that window, I just discard that event. Now, the last thing that you have to define is what you actually do when you trigger. For instance, if the late triggers are coming in, are you doing accumulating fired pains, which basically means you keep all elements in your window and you do the complete aggregation again. So if you have, for instance, in sum, when you do a late trigger, you do the complete calculation again. Now you have other trigger modes where you basically only do the difference. So if a new element comes in late, you only emit the difference to the prior result that you had. That's not always possible for all calculations, so you have to see which one you use. Again, anything else stays the same, so you don't have to change any other parts of your code. So that is where the how comes in. So in our case, we do, and I have to add like some typing here. Right. So in our case, what we do is, I want to have like 5-minute windows. I'm gonna trigger after it's closed, but I also want to very early, like I don't want you to have to wait 5 minutes till you see your player stats or the team stats. So what I'm doing here is after processing time past first element in pain, which basically means after the first element in that window, after group the first element into that window that I defined, my 5-minute window, 10 seconds after that, I emit the first result. And then every 10 seconds, I emit results for that window. So I get like throughout the 5 minutes, I get every 10 seconds an estimated result. I also allow for late firings, and I also want to already emit results, new result, updated result every time a late element comes in. And I allow for the window to stay open 10 minutes after these 5 minutes, like after the last element that I grouped in this 5 minutes. And I do accumulation. So every time I do the complete aggregation again for all the elements that I have in my window. So now hope that this pipeline works actually. I'm gonna try and deploy it. So this comes all with Maven support and everything. But wow, yay, of course. Okay, I have some, let's see, we have the, does anybody spot the mistake that I have in here? Let's see. Then a window, the trigger comes in, yes, that should be fine. I start, oh, no, that is all right. Then I close this, that should be, oh. Line 54. Let's see. Did I put something? Oh, I know what this is. All right. Worse. Let's cross fingers. Build success. And seems it's doing something. All right. So what you see here is no. Oh, come on. Okay. I know what my problem is. I did one thing. I didn't clean up my demo workspace before. Rookie mistake. So what just happened is basically I pushed all that pipeline. It was packaged and sent to Dataflow. Now I can name my pipeline, and what Dataflow doesn't allow is that I push pipeline with the same name twice. So I have to, of course, to cancel my pipeline first before I can submit it again. And because I don't want to wait that long, I just give it a new name and just apply it while the other one is canceling. Now the thing is, what you don't see here is what I didn't have to define or anything. You can inspect my code like to everything. Is I didn't define like how do I deploy my machines or what do I install on the machines. It's all done for you behind the scenes. The only thing that I defined here in my arguments that you see here is that like, okay, what runner do I want to have? So you can use a direct runner if you want to run it on your laptop, or you can use like a Spark runner, for instance, or a Gear Pump runner. So depending on the underlying system that you have where you want to run your pipelines, you define basically the runner that you're using. The second thing that I want to point out here is that I said it's streaming. So you, as like I show in a minute, is you can do streaming and batch. So in this case, I have a streaming pipeline, so I am putting that to true, and then I say how much machines I want to have initially. So what you can also do with Dataflow is it supports auto scaling, so you can basically put boundaries on how many machines you want to have. And then the other thing is like the zone and if I want to update my pipeline. So I could have let my pipeline run and just used update true, and then I would have updated the pipeline, that would have been another option of what I could have done. So let's go a little bit smaller here that you can actually see what is happening. So you can see here that I deployed my pipeline, and in the Dataflow console, you can see like all the steps, the logical steps that we are doing. So we are reading from PubSub, we are windowing, we are also archiving to BigQuery. Then we are keying by team and calculate all the stats and write it to PubSub and BigQuery. And we key by player and write that to PubSub and to BigQuery. So let's have a look at the game. So if you want to play, and that would be lovely, you can go and scan that QR code or type in that short link down there in your smartphone. And I'm gonna do the same as well. All right. So what you get is basically, you will see it on your phone, but you get basically 4 fields, so 4 round fields. And I, of course, can show that here as well. So it looks a bit more beautiful on your phone than here. You get assigned a color. So in this case, like I get green, and then I can start clicking green. And if my pipeline is running, it should at some point, I should see a result coming up. So that is the estimated result. Let's hope the demo works. You can see if the pipeline is running. Oh, it's still starting. All right, it's slowly starting. Give the system lag of 5 seconds, it should be fine. Yeah, okay, cool. All right, so you see, like I'm pretty bad with 38%. We don't have anybody that plays red, unfortunately. Okay, so what you see here is like we do the windowing by 5 minutes, but as you can see, the updates are much faster. So that are our 10 seconds triggers that we update this data. Now, what I want to show quickly is I'm using the exact same things for my batch pipeline. And my batch pipeline is really, really small because I don't do the windowing. I'm not working with streams, so I don't have to do the windowing. So in this case, I read all, like as I mentioned, I archive all the data. So I read from that table, I key by team, I group it by team, and then I calculate the team scores. So now it would probably take too long to run this, but I'm going to show you really quickly how that looks like in the end. I have 10 minutes? I have 10 minutes left. Cool. So let's see how that looks like for batch pipeline. So this starts my batch pipeline. And as you can see, what I omit here is the streaming. Again, I don't do an update here, but my last batch pipeline finished, so it should still succeed. And all the other things stay the same as I used for my streaming pipeline. Again, if we look at the code here, I completely reused the code of my streaming pipeline. I didn't do anything else. Like if I learn this system through rough, I basically can do batch and stream processing in one model, and that's exactly what we want to achieve with Apache Beam. Now, what I'm going to use to show you how the data looks like is BigQuery. So let me open up BigQuery quick. So BigQuery is our data warehouse analytics tool. It's basically a column store where you can process and run queries over terabytes of data in seconds. Now the first one, what I want to show you here is we have this collection color smash, and here we have like all the data that comes in. So if you look at the preview, you see here the only things that I collect is the timestamp, the UID that I generate in the application, the team that you're playing for, the color that you hit, and the device. that you had if you played on desktop or on mobile. And if you go to last, we should see a lot of mobiles here. Yes. So you see also here the timestamps is pretty accurate to what we see right now. Now the player stats is where like all the data that I aggregate and calculate, I on the one hand push it to PubSub so that you can see it on your phone, and that could be, for instance, like if we go back to the improving your user experience, you can basically build a pipeline where you take this insight to improve to guide your users to certain parts of your application, or you show certain promotions based on what the user is doing in your application. So how does this look like? So what I'm collecting here is basically, again, the timestamp of the window when that triggered, the team, how many points that team had, and then the ratio, the device, and when this firing was. So you also can inspect and get the information of the triggers. Was this an early trigger, or was it an on-time trigger, or was it a late trigger? So you get that information downstream in your systems, so you can handle these results in the right way. And the same here, the team stats, where we basically calculate the rate, the hit ratio per team. So let me have a look if my pipeline finished. If my pipeline finished, that I probably can show you. Yes, so it finished, so we can check. So one of the queries that I want to show, let's use this one. So what I do in this query, so what I put as an element in my, let me make that a little bigger. Now the batch, if I do batch processing, I don't have any timing information. There are no triggers or anything. So I basically populated that field with all time. And now you can see like that I just calculated, oh, let's go to the last. Okay, that hasn't come through yet. So I basically calculated the aggregate of all time. So I have done this game like a couple of conferences, and in total we have over 40,000, I believe, elements now in the system. So if you look at the system, we have like 41,000 events that happened, and now I do all the aggregation and see basically what is the mean hit ratio, and we can see that red is currently the leader in the all-time calculations. Now back to the slides. So basically, patch pipeline was reading from BigQuery, running it through Dataflow, and then writing it to BigQuery again. Now I mentioned earlier that you can run Beam models on multiple runners. We have Dataflow, Flink, Spark, Apex, Gearpump is coming, and many others. You can see what, like in this matrix, you can see basically the capabilities based on the questions that we ask. So the what, where, when, and how, and what is supported by the different runners underneath. So with this, I want to open up for questions, and thank you very much for your attention.